Hello and welcome back to Dr. Logic Awkwardly Does Logic. In this video, I'm going to prove to you Lindenbaum's lemma. This is one of the most magical lemmas that I ever came across as an undergrad. It's still not my favorite lemma. We're going to get to that one in a couple of videos, but this one is really quite remarkable. It also involves rather a lot of kind of heavy set theoretical lifting. So there's going to be a lot of details and a lot of kind of technical steps along the way. So apologies in advance for what could be potentially a very dull video, but actually proves a really, really cool result. So while I get the whiteboard up, I'm sure that you are all sitting here going, okay, but what exactly is Lindenbaum's lemma and why do we want it? So we had gotten something in the previous video about the relationship between theorems and maximal consistent sets. Lindenbaum's lemma is going to give us something on the other side. It's going to say us something about non-theorems and maximal consistent sets. So the result is this. And even though it gets called Lindenbaum's lemma for the lovely alliteration, it's actually an important enough result that we're going to call it a theorem. So the theorem is this. Any S consistent set of formulas, gamma, can be extended to a maximal S consistent set. So it can be extended to a maximal S consistent set, which we will call lambda. So another way of saying this is if gamma is S consistent, there is a lambda such that gamma is a subset of lambda and lambda is maximal and S consistent. So on the one hand, this might seem like a fairly straightforward kind of result. On the other hand, the reason why this is an important thing to prove and why it's not necessarily as straightforward as you might think it is remember what theoremhood and consistency is about. It is about provability within a set. What are we able to prove and what are we not? And proofs are always going to be finite. However, maximal S consistent sets are infinite. And so what we're going to be doing is we're going to build up a process that essentially says, okay, if we've got consistency here and we do another step, we've got consistency here and we do another step and we've got consistency here. If we do this an infinite number of times, we won't somehow smuggle in inconsistency accidentally without knowing it. So that is what we are going to be doing. So how do we prove this? Well, we are going to start off with some S consistent set gamma. So let gamma be a set of S consistent well-formed formulas. What we are going to do is we're going to construct a series of sets starting with gamma and ending with lambda, our maximal set. Now, because the language that we have has a countably infinite set of atomic propositions, this means that because every formula that we can construct from these atomic propositions is finite in length, we only have countably infinitely many formulas that we can have. So this is an important point. If we were working with higher levels of infinity, we would not be able to get the result that we need. So there are only countably many distinct, syntactically distinct modal formulas. Given that, the first thing that we are going to do is make a list of all of them. So make a list of all the countably infinite, distinct, modal, well-formed formulas and put them in some order. it doesn't matter which, but what we're going to have is a series of formulas, phi1, phi2, phi3, and so on ad infinitum. We will then define a series of consistent sets, lambda 0, lambda 1, lambda 2, in a consistency preserving fashion. So we'll define it as follows. So we are going to just let lambda 0 be the set gamma that we started off with. Then we will define lambda n plus 1 to be the set from the previous stage, lambda n, union the n plus 1 formula, so phi n plus 1, if this is consistent, and if not, then we will let lambda n plus 1 be lambda n union the negation, so not phi n plus 1. And then what we need to show is that if lambda n is consistent, lambda n plus 1 is also consistent. So that is where we're going next. So we need to show that if lambda n is consistent, then lambda n plus 1 is also consistent. And the way that we are going to prove this, so we've got kind of like a proof within a proof, is contrapositively. What we're going to show is that if lambda n plus 1 was an inconsistent, the only way this happens is if lambda n was already inconsistent. So we will show that if lambda n plus 1 is inconsistent, then actually lambda n was already inconsistent. So in a sense, what we're showing is that the inconsistency didn't get added at this step. So suppose that lambda n plus 1 is inconsistent. So if this is inconsistent, then what we know are two things. We know first that lambda n union phi n plus 1 is not consistent, and also that lambda n union the negation of phi n plus 1 is also not consistent. Because if it were, then we would have had something that was consistent. But we're working under the assumption that we don't. Now, I'm going to have to bring up a new whiteboard, but remember these two things. So we've got our first fact that lambda n union phi n plus 1 is inconsistent, and that lambda n union not phi n plus 1 is also inconsistent. So these are the two facts that we have. What do these mean? So if one is the case, i.e. that the set union the formula is inconsistent, then just looking at the definition of inconsistency, there are well-formed formulas delta 1 to delta n, which are in lambda n, and we can prove in the system S the negation of all of these deltas. So delta 1 to delta and phi n plus 1. That is just stating what the definition of inconsistency is. Now, we can run the same thing for the other thing. So if 2, i.e. if lambda n and the negation of that sentence is inconsistent, then we know that there are going to be well-formed formulas gamma 1 up to gamma n that are in lambda n. And again, in system S, we can prove the negation of the conjunction of all of the gammas and the negation of phi n plus 1. So this is, again, just a restatement of what the definition of consistency means. Now, we can take these results and do some propositional reasoning on them. If you can't have the conjunction of everything, then if you have all of the deltas, but you can't have all of the deltas and phi n plus 1, this means that phi n plus 1 has to be false. So if all of the deltas are true, then phi n plus 1 is the one that's got to be false. And similar reasoning from the other one is if all of the gammas are true, then it can't be not phi n plus 1 that is true. So that one has to be false. So we've got not phi n plus 1. Or let's just make it easy on ourselves. By double negation, we know that phi n plus 1 has to be true. Now, what we then can see is that all of these are in lambda n. All of these are in lambda n. So lambda n can prove all of the deltas and all of the gammas. And if we've got all of these, then we have both phi n plus 1 and not phi n plus 1. But this is just the same thing as saying you can't have all of the deltas and all of the gammas together at once, because if you did, you would get a contradiction. So, combining these results, we then know that it is that you can prove in S that we don't have the conjunction of all of these. But each one of these are members of lambda n. So what we have shown is that lambda n was already inconsistent. If we were not able to add either phi or its negation to the set in a consistent fashion, the only time that this can happen is if there was already an inconsistency in lambda n. And going back to our initial assumption, we are starting off with a set gamma, that's our lambda 0, which is consistent. So if we start with something consistent, we will not bring in anything inconsistent. If an inconsistency shows up at some stage, it had to have been there the stage before. So this is all of the stages that we have. So we've got our, remember, lambda 0 is just gamma, and all of the lambda n plus 1 are constructed by potentially adding phi or not phi at each step. Now, I say potentially because it could be that we come across a formula in the list that was already in there because it was in our original gamma, in which case we take the union, the set doesn't change, but that's okay. That doesn't affect things. So this gets us our basis case and each individual step. What we need to show, though, is that there is an ending to this process, that eventually we get through all of these countably, infinitely many modal propositional formulas in the list that we had. So we're going to define lambda, this is our target maximal consistent set, to be the union of all of the lambda n. So the union of all the lambda n. So once we've gone through our entire list, we then just take all of the sets that we've constructed and put them all together into one great big set. Two things then that we need to show. The first is that lambda is consistent. If it were not consistent, then there would be a finite subset of it that was inconsistent. So if it isn't, then there is a finite subset of lambda which is inconsistent. But every finite subset had to have been constructed in one of the lambda n's along the way. Every finite subset occurs in one of the lambda n constructed along the way. So that means that if the entire big union is inconsistent, there's a finite subset of it that is inconsistent, and it is in one of these lambda n's constructed along the way, which means that lambda, so call it lambda I, is already inconsistent. And then by what we just showed is that the only way that lambda I could be inconsistent is if our original set gamma was inconsistent. But by hypothesis, it is. So that is the first thing that we need to show. The second is that this great big union of all of the sets is, in fact, maximal. So if it isn't, well, what's the definition of maximality? Then it means that there is some phi I such that phi I is not in lambda and not phi is not in lambda, so not phi I. But phi I was in that ordered list of sentences. So it's something that, so it's in the list of well-formed formulas that we used to construct the interim lambdas. So lambda I was constructed either by adding phi I or by adding not phi I. But whichever one of this it is, this contradicts the assumption that neither of these are in the big lambda, but the big lambda is just the union of the smaller lambdas, and this one is going to have either phi I or its negation. So either phi I is in lambda I or not phi I is in lambda I. And since lambda I is a subset of lambda, this means that either phi I is in lambda or not phi I is in lambda. So this is Lindenbaum's lemma and its proof. This becomes important once we move, as I said, to the kind of flip side of the result that we had in the previous video. What we want to show is that if you have something that is not a theorem, then there is some maximal consistent set that contains its negation. This is actually going to be a super straightforward corollary, but I'm going to do it in the next video because this one has gotten rather long and full of lambdas and phis and psis and gammas. So I will leave you to digest this, and we will come back for the final corollary and the very last thing that we need to define the worlds in our canonical models. So join me then, and until then, take care. Cheers.